charge of our sales and marketing, and we have our VP of hardware and one of our top chip architects here as well to join us, although I think I'll probably end up doing a fair amount of the talking here today. The things I'd like to go through don't have a tremendous amount of time, but we'll go into this, and I'm sure there'll be some interesting questions proposed at the end. I'm going to go in a little bit into into our company, like what is our vision, like what are we doing? Talk a little bit about the platform that we've created, the open platform that we are proposing, and what you can do with it, and we'll give in the middle sort of a demonstration of it functioning with this hardware, which I'll get into, and we'll also then go into a little more detail on some of the problems associated with this, and how some of those problems may have more general applicability even beyond producing images. We feel there could be more general applications of what we've invented here, and then do some Q&A. So, what is the vision of Caustic? It's essentially today to do very high quality image reproduction. This is done using a technique called ray tracing, and it's traditionally a extremely slow and expensive offline process. Now, in recent years, there has been some development in increasingly trying to make ray tracing faster and gradually towards interactivity. But those efforts, if you compare them visually to what you see when you go to the movies, there's still a phenomenal gap. And what we're going to get into is a little about why this is and why we believe we have the solution to that. We view our technology as essentially, there's going to be a convergence between the techniques of doing offline production rendering and interactive graphics, and we believe that that's extremely soon. And there's a few breakthroughs are needed to make it happen, but we'll go into that. Our company, we enable interactive graphics, cinema quality graphics at high speed. We were founded in 2006, and our headquarters are up in the city, so we're located up there. About 32 people, most of it's engineering, pretty much even split software hardware design. And we have about 16 patents filed so far, and we're continuing down that path because we're opening up a pretty new space here. And we're privately funded right now. The future of 3D graphics, like where's it going? There's a lot of people who debate about, is rasterization a better way to produce an image, or is ray tracing a better way to produce an image? We're not going to put a stake in the ground about which is a better way to produce an image, because today it's not practical to use ray tracing for interactive graphics, so it's not even a debate. However, if ray tracing were extremely fast and the programming interfaces were familiar and standardized, it's our belief that people would be using ray tracing a heck of a lot more to synthesize images than they do today. Ray tracing has a number of benefits. It can have better image quality. But it's the easier content creation model that's the thing that really got us excited, because you can make beautiful images with rasterization if you put enough artist work and enough tricks and hacks and engineering work into it. You can make it produce great images, as many have seen from looking at today's games. But behind the scenes, there's a colossal amount of work going into pre-baking information and faking a lot of that stuff. And it's our belief that it's the combination of the promise of higher image quality from ray tracing, but the easier content creation model that is the very exciting part of it. And it's our belief that once the technology is there and available to the majority of people, that most interactive 3D content will be ray traced. A lot of you may already know basically what ray tracing is, but I'll go into a little brief description of that. So, rasterization works by essentially taking your geometry, your 3D description of the scene, taking those triangles and kind of projecting them onto 2D space on your display, figuring out what pixels are covered by that triangle, and then either going down in what are called scan lines or tiles, and essentially each of those pixels or fragments, as they're called, are mapped basically to a very wide parallel processor, and shader programs are run for each one of those pixels to figure out what color that fragment needs to be. And this process continues. You go through all the geometry, and you end up painting onto the screen in 2D screen space. You essentially are painting triangles onto the display. Ray tracing works rather differently. What ray tracing does, pardon this silly build, let me go through here, is essentially what you do is you iterate through all the pixels on your display, and you create sort of like a model of a light ray. So that light ray has an origin, like comes from somewhere, has a direction vector of where it's traveling to, and you can set other things like how far you're going to allow it to go to, and also you can have other data carried along with that ray as well. And what you do is you let the ray cast out, and your question you're asking the algorithm is, what is the nearest object to that ray's origin? You figure that out, which is a caustic process. Once you've determined that, then you execute the shader to evaluate what the material on that surface is. The neat thing about ray tracing is that those materials can in turn generate more rays and continue to cast them. So the beauty of that is that things like reflections, refractions, shadowing, a lot of different types of effects that we're very used to in the real world are much easier to recreate, because you can actually determine visibility between objects inherently. With rasterization, there's no such physical model existing. You're kind of taking the 3D world and squishing it into two-dimensional space and painting onto the screen. So there's a lot of tricks to try to make video games look good today. With ray tracing, it is a little more natural to develop for and create artwork and shaders for. Now, ray tracing is a fairly straightforward problem to accelerate if you consider only the initial rays coming from the camera. These ones right here, pretty easy to map to a GPU today. However, if you look at what happens, ray tracing's inherent value is in its ability to cast what are called secondary rays, and lots of them in very random directions. So what you end up with is a phenomenal number of these rays traveling in very different directions inside of the scene, and each one of those needs to walk an enormous database to figure out what the closest triangle to the ray's origin is. Then once that has been determined, you need to then execute a shader at that ray's intersection point. And this is a very tough problem to parallelize because of the incoherence of it, and because of the essentially random order that falls out when you start producing really high quality images. So I don't like triangle diagrams, but I'll be very brief on this one. What is Caustics? How are we going to make money? Well, the answer is, well, we're selling these hardware devices to particular markets. Our first market that we're going after is professional 3D. So people like architects, industrial designers, and also people who work in the film industry who need to pre-visualize the animation or the sets that they're going to do before they actually send them out to a render farm to produce the images for. So those guys already understand ray tracing and why it's valuable, so you don't need to sell them on why they should switch to ray tracing, because they already use it. So it's an easier, we have one fewer problem to tackle in that space. So that's what we're initially looking at. We believe, though, that with the appropriate advances in our ability to fabricate a more compact chip, we're going to move this towards gaming. There are a lot of other interesting markets that this can be applied to, as I want to get into in this presentation, because what we have is a very general solution to a database problem that we think actually might have applications outside of rendering. So, not all ray tracers are created equal. So, today's current approaches for accelerating ray tracing tend to basically end up with highly reduced image quality, and the reason for that is it can't generally accelerate anything past the primary rays or some extremely simple shadowing. So the big thing that we have going is that we're able to actually take full advantage of general compute hardware and our hardware, and we're able to saturate it even in cases where the rays are traveling very randomly. So effects such as global illumination, where ray hits surface and you want to integrate the lighting at a particular point, you need to shoot, sometimes hundreds of rays in random directions to be able to integrate the incident light at that point. That's true global illumination. It's very hard to accelerate that, but we excel at it. Soft shadows, where there's very subtle shadowing going on here. That is another case where you end up needing to shoot a lot of very scattered rays. Glossy reflections. Depth of field is another big one, where you actually might want to model a real camera lens. And again, you do that by taking random samples on a lens model. So again, it involves random numbers and shooting a lot of random samples. So you end up with a lot of very incoherent rays to produce those kind of images, and it's that case that we're good at. Ambient occlusion is another big one. It basically is kind of like shadow rays, except they tend to be a little shorter, and it's used to try to figure out, if you have an object with sort of like a sculpture and it has folds in it, the things get darker in those folds. That's something that ambient occlusion is used for. And actually, if you look at games today, they tend to do ray traced ambient occlusion not on the client's device, but they do it offline in the game production process, and they bake those ambient occlusion maps into large textures, which are then looked up into by the shaders running in the rasterizer. So we actually think our technology even has application before it ever ends up in a game console. We think it can really help the production processes of those games or other things potentially here, like Google Earth. We actually think there's applications potentially for pre-baking lighting data using ray tracing, which could be pretty interesting, and today we would have a very compelling solution for. Caustics, these dense focus points of light, are another area where you need to shoot a lot of very scattered rays to recreate. So what have we solved? I've went into this to some extent. If you look at today's GPUs, they're very fast devices indeed. However, if you try to program one of these things, you realize that you basically have to be running the same program over and over on a large block of data elements that all need the same basic set of operations to be performed on them. If you give it a stream of data and ask it to run a completely different computational kernel on every other piece of data, GPUs are a lot slower than CPUs. They only work well whenever you can gang together large amounts of data that all basically needs the same instructions to be applied to it. And we can maybe talk in more detail afterwards about the detail. I want to keep going in the presentation, but it's that issue of being able to saturate compute hardware that we've been able to solve for scattered rays. The other issue is that cache hierarchies, where you've got a very large scene, you've got a lot of parallel compute elements trying to trace rays. If there isn't locality of reference, you may as well not have a cache, because you're going to be basically fetching from your system's DRAM, or worse still, disk, all of the different textures, shader code, and geometry data that you need to do the ray tracing. So the algorithms that we've invented are able to extract locality of reference from the ray tracing problem. And that algorithm is implemented in a small coprocessor, which basically attaches to today's big computer arrays. So we actually do, despite the fact we've built a coprocessor, we actually are leveraging commodity compute hardware, contrary to what some people think, that we're building a new type of GPU. That's really not true. Our hardware is nothing like a GPU. It has no similarity to it at all. So we do leverage existing compute hardware to do the shading. So the code that you run once the rays intersect objects is running on today's graphics hardware. The other big thing is, if you look at ray tracing and compare it to rasterization, ray tracing is a highly immature technology in a weird way, because people used to all write their own rasterizers by hand. The underlying hardware would be different. People would write their rasterizers in machine code by hand. But it got to a point where people realized that was a bit silly, and they wanted to build custom hardware to do it. So industry standard interfaces, OpenGL being one, DirectX isn't really an industry standard, but a lot of people use it. These two platforms got created to allow game and interactive application programmers to stay abstracted from that hardware and write their applications at a slightly higher level. Ray tracing is not like that today. If you look at Mental Ray or Brazil or other types of big offline production ray tracing packages, you know, the shaders are all written in C++ and they're just linked in. They're just big monolithic blocks of code interspersed with machine code to do ray traversal on whatever architecture they're running on, which today is pretty much just the CPU. Ray tracing hasn't undergone that sort of step where an abstraction layer has been created to allow rendering packages to sort of be abstracted from the underlying hardware. We believe that this is extremely important for ray tracing to be more broadly adopted. So what we've done is we've figured out how to take the OpenGL API and add a fairly condensed set of extensions to it to allow you to be able to cast rays inside of an OpenGL application with a very, you know, mellow learning curve. And the other area is the ability to handle dynamic scenes. So let's say you could trace rays, you know, phenomenally fast. Artists are going to want to start picking objects up and manipulating them and actually changing them, not just moving the camera. So that database that's required for a ray tracing system, whatever kind of a database it is, had better be quick to be able to update, or it's kind of not going to be useful for interactive applications. So we about 3 months ago delivered our platform and our coprocessor in a box to a number of developers who are now building it into their pipelines and building some custom applications on top of it. So our platform, to basically go through its layering, essentially you've got the Caustic coprocessor, which basically used in tandem with your existing multi-core CPU or a GPU produces the images. And you program this through the Caustic GL interface. It looks just like OpenGL, except you can cast rays now. And then basically rendering clients are things like those big slow offline ray tracing packages. Similarly, interactive applications. So let's say you wanted to build an interactive ray tracer, an interactive ray tracing system. Our vision would be that would be exactly the same as an offline ray tracer used in a render farm. The only difference would be they might turn the sampling rates down for their integration and shoot fewer rays. But other than that, why should there be any other difference between an interactive application and an offline renderer? Our vision is that they'd be the same. And today they're not. Today, you know, film studios, when they want to do pre-visualization, they sometimes use game engines to do that, and that's all rasterized. But then they get really angry when the graphics don't look as good as what they get when they actually submit it to the offline ray tracer. So what is the Caustic One card? Basically, I've already sort of described this, but it's a PCI Express card, plugs into your computer. It's powered by the bus, fits in a single slot. And it's FPGA based today. We essentially took our ASIC design and scaled it down by about a quarter and reduced the clock speed, and that's what we've put on our FPGA cards for now to get this in the hands of developers and start getting applications written on top of it. And even with with these FPGAs, there's still a very large speed gain to be had using this versus just doing everything on the CPU. So it's a developer product, essentially, for 2009, not an end-user product. We're not selling this to artists today because the applications have to be written on top first for it to be of any use. Our hardware basically deals with the massive acceleration of incoherent rays, and it also deals with things like photon mapping as well, which I'll get into what kind of database operation that is. But you could think of our hardware as kind of like a massively parallel scheduler, which basically offloads the ray tracing problem, offloads all of the database side of it, and then essentially schedules work for whatever CPU or GPU you have in your system. Let's give a demonstration of this. So basically what you're going to see is just an application. It's running on Mac OS X right now. This app is, it's got a Cocoa user interface, and it's written directly on top of the Caustic GL. The cool thing about this is that, anyone who knows OpenGL could sit down and write something like this in a few days. It's really very, very easy to program, and that's the cool thing about this. You don't need to become you don't need to start writing low-level code to get this kind of performance with the system. So let me go through a little bit about the scene configuration here and show you what we've got here. So basically, this scene that you're seeing has 5 million triangles in it. These two cars, about 1.6 million each, and then the rest of the scene geometry makes up the rest of the 5 million triangles. How the scene is set up, basically, there's in our OpenGL we have two programmable parts of the pipe. Well, in addition to vertex shaders, we have ray shaders, it's a GLSL shader that runs once rays intersect objects, and that's how you define the material. That's how you program what the material does, and it can in turn emit more rays or access the frame buffer. And then we have a thing called a frame shader, which runs at the beginning once for every single pixel, and it's in there that you can start shooting the initial primary rays into the scene. So what's happening right now is every frame here, the frame shader is running once for every pixel and setting up the rays. They're going out into the scene. They're getting ray traced on our hardware, and the rays are basically constantly being reordered during their traversal to decrease the memory bandwidth access to the scene, and then they're being scheduled to this multi-core Nehalem CPU to be shaded. So our Caustic GL essentially compiles those GLSL shaders into SSE code chunks, which are then mapped out to the 16 threads on this 8-core system. So as I move around, you'll notice in the scene things that you can see the reflections there between the two cars. If you can see it in the projector, that would be an effect which in a rasterizer you would have to. It would be quite difficult to produce self-inner reflections between two objects which are right next to each other. You can kind of fake reflections of a very large environment by putting it into a texture map and looking up. But here, we just create a ray off the car paint and reflect it over, and it'll hit the other car, and so forth. You'll notice the tail lights on the cars. If I go over and take a look at those are not a texture. Essentially that's just a bunch of geometry defining the tail light, and we have a shader which refracts rays and one which reflects rays, and we put some bulbs in there, and the image falls out of it. Now you'll notice the shadows here. What's happening is, the ground itself, the shader's doing it's all trilinear filtered textures, so we're doing mip mapping, and I'll go into a little more detail on with some pretty cool ways of doing that. What's happening is you can see the shadow there. No need for shadow maps in this. You just create a ray inside the shader and shoot it towards the sun in your scene, and you'll get self-shadowing for free. It happens. It's very easy to do that. But you'll notice it's still just a hard-edged shadow, and it wouldn't really look that way. So the cool thing is, if we go in here and I select this, what this is now doing is I've quadrupled the number of rays that were cast. So we're now up to an average of about 10 rays inside of every pixel. So what's happening is now instead of shooting one shadow ray towards the sun, we're doing 2 samples of ambient occlusion at every intersection point, so 2 randomly cast rays to figure out the visibility of that point to the ambient lighting in the scene. And we're additionally shooting 2 directed but random shadow rays towards the sun, so you get sort of a soft shadow being created. Now, what happens is, when you do ray tracing, the way you do this integration is you use a table of random numbers generally to figure out how to direct those rays within a certain range. And it's done like you would expect. It's just the random numbers we put inside a texture map, and we sample it in the shader and set up rays to go out into the scene. Now, you'll notice here, this is the sampling rate. So if I were to go to there and increase that, now what's happening is you see the noise went down. So essentially all that happened now, we're shooting eight randomly directed shadow rays towards the sun, and then 8 randomly directed ambient occlusion rays, and that stuff just falls out. And of course, if I were to start moving the objects around, the shadows all just self-update. There's no tricks required, it just works. So if I go over here, and you can really see the ambient occlusion effect over here on the fountain. If I go back to just naive lighting, that's just a shadow ray being cast towards the sun. So you're either in direct sunlight or you're not. But over here, when you switch on the ambient occlusion, suddenly now a lot of the surface detail starts to come out. You can actually see that it gets darker in the folds where it'll be less exposed to sunlight. And again, you turn up the sampling rates, and the noise goes down, and you get a nice solution in the image. Now, a few other things to look at in this system. Oh, I went inside the car. Is the shading system. So if I go to here, and let's take a look at this car here, the car paint itself. So if we look closer at the car paint, it's actually a fairly complex shader. We're using pearl and noise to create a paint flake effect. So there's obviously the reflections are coming off, but the shader itself is fairly complicated. So if I were to go over to here, and this is a list of all of the objects in the scene, and I were to look for the body of the car, in this drop down, all this is basically a list of text files which contain the ray shaders which define the material on that surface. So if I go to here, obviously there's a whole bunch of parameters which I can adjust. So if I wanted to say, adjust the where is it here, diffuse color, which is the color of the car paint, obviously I can make those changes on the fly there. That's just changing settings to the shader. But in more detail, if I go and hit edit here, this is just straight up GLSL code. So people who've programmed OpenGL before and written shaders will be incredibly familiar with this. There's the uniforms defining all of the settings of the car paint, and here we actually are doing water droplets on the paint as well. So there's a whole bunch of stuff in this shader. It's fairly complex. But let's say that I want to make the paint sort of have some holes in it. So I want to make it that there's a pattern on the paint, and sometimes the rays go through it, and sometimes so it's kind of like someone has taken a buzzsaw to the car paint and cut some wavy holes in it. In a rasterizer, this would be quite difficult to recreate that effect. In this, it's extremely easy. So let me zoom back out from the car a little, and let's start typing. So I'm going to generate a signal here. So as I'm typing, what's happening is our OpenGL implementation, what we're doing is we're constantly calling upload shader string every time you press a character, and then our runtime compiler is generating SSE code as we type and submitting it to the multi-core CPU for the shaders. So if I keep going, I haven't actually affected the look of the image yet. Accumulate. So what that is doing right now is that's just showing pearl and noise being directly visualized. So pearl and noise, for those who aren't familiar with it, it's basically just a waveform that's random but smoothly varying, and it's a very useful building block for generating what are procedural shaders. So like you can use that random noise signal to position, say, leaves on in a forest, and you'll get a random distribution of those leaves, or you could use it to create wood grain, or you can use it to do anything you want. It's like a random signal that's used a lot for procedural shaders. Now, what I'm going to do is I'm going to use that to figure out where the holes are going to be. So I'm going to take that float n, that n variable, I'm going to take that and I'm going to cut it. Now what that's doing is it's saying that anything below 0.2 goes to 0 and anything above 0.2 goes all the way up to 1. So you're either all on or off. And that is going to be a function which I'm going to then branch on in the shader. And if I'm in n equals 1, I want the car paint to do exactly what it was doing. Otherwise, I want it just to create a ray that goes straight through. So let's comment that out, because that was just to see what the signal looked like. Now I want to say if n is greater than 0, then do something in return. There we go. So now I've got the cases where n is not greater than 0 doing the car paint like it was before, and otherwise the shader's just returning. But I want to go in here and I want to create a ray. So create a ray, emit ray, So the default behavior is for the rays just to inherit the incoming ray. So this shader was triggered by a ray hitting the surface. So by default, any further rays you create, their origin begins at the intersection point with the material, but they inherit the direction. So you can see right now, looking at the car, you notice the rays are kind of going through it, and I can see the interior of the car itself. Now let's say I wanted to reflect the rays off that area. So let's change the outgoing ray. So I can go to here and say GL outray dot direction. I'm going to change the direction of the outgoing ray. I want to reflect it out. I don't want it going through. I want it to reflect back. So GLSL's always had its reflect function. It just takes a vector and a normal and figures out what the reflection would be. So I'm going to reflect the incoming ray direction with normalize the surface normal. So now I've got reflections coming off, and now I want to make the reflections a little darker. So I want the outgoing ray color to be the incoming ray color down by quarter. So now I've got like shiny blobs on the car paint, right? But actually I kind of liked it better, just see-through. But anyway, so you get the idea. So now, of course, if I were to go and pick up the car body itself, lift it up, you'll see that, right, that stuff just falls out naturally, and you can see the shadows all updating, all on the fly. So it's very, very easy to program this, and you can sort of imagine creating an awful lot of things a heck of a lot more quickly than you might be used to doing graphics with OpenGL. Thanks. So a few other things to look at. Okay, let's imagine we wanted to do things like reflections that aren't just like perfect mirrors. Everything you've seen here is a perfect mirror. So I'm going to go here and say there's another object in the scene which is hidden right now, and all it is just a few triangles on the floor to create a big ground plane. And there's a shader assigned to that right now that called Specular Glossy. Now, a mirror shader is actually really, really easy. I just sort of did one. You just take the incoming ray and reflect it. But let's say I wanted a not so perfect reflection. I want it to kind of look like brushed metal. So the shader itself, there's a table of numbers, kind of like I've been doing for all those other glossy effects like shadows and stuff. There's a table of numbers called the Halton sequence, which is a popular QMC sequence, which is used for generating random numbers for sampling, and it's a good sequence because you can have any number of samples, and it's always going to tend to give you a pretty good unbiased sampling. But if I go in here and set the number of samples now, let me see. I want to start with 2 samples. And gloss focus. So what's happening now, the gloss focus, if I set that to say 0.97, what's happening now is it's shooting 2 reflection rays off, but there's like a cone of discrepancy, so they're becoming more glossy. If I were to put that down to like 0.9, it becomes a more glossy surface, and then up the sampling rate to say, I don't know, 6. Now you're starting to create sort of imperfect reflections. There, it's sort of, you see, it's kind of like a hazy reflection now. So off the floor now, anytime rays have been hitting the floor, that one incoming ray has resulted in 6 outgoing rays that are very slightly offset from each other. And there you go, glossy reflections, and no problem. Very, very, very easy to do. Now, you can imagine when you start having fun with this, doesn't take long before you start spending rays like crazy, and it will obviously become not so real time. But the big thing is that our system is able to saturate a lot of very wide SIMD hardware, even in cases where the rays are extremely scattered. So we're able to keep the acceleration up, whereas if you look at the other real-time ray tracing demos out there, they're not showing you these kind of effects because their hardware falls on the floor when they try to do it. Now, let's do a few other things like that. Lenses are pretty fun to play with. So let's say I want, you'll notice everything's in focus right now, and in a rasterizer it's that way too, because it's basically modeling a pinhole camera where all of the rays are kind of originating at one point. What I want, I can do things, I obviously adjust my field of view and so forth, but you know, if I were to take a photograph of that with a real camera, depending on the size of the aperture setting I was at this point in time, that nearby object might be out of focus, and I might be focusing on different levels of depth. So let's say I wanted to mimic that. Well, what this is doing is it's switching to a different GLSL program, different frame shader. And that GLSL program is now selecting random points on like a thin lens, and then figuring out how the rays would refract through the lens at that point and setting the origin and direction of the ray based on that. So now it's kind of out of focus, and I'm only taking 2 samples, so it's kind of grainy right now. But I'm going to adjust the focal distance, so I'm focusing on the red car right now, and you'll notice the foreground's kind of out of focus. Focal blur, this is like changing, see my depth of field is narrowing and getting longer. You know, if I go to a very, you know, it's a spherical lens model, so there's a proper, you know, really wide angle lens. Now, if I want rid of the noise, well, that's pretty easy to do, just take more samples. So if I go to, let's get it like that, and if I were to punch in 6 there, you notice it, you know, the random noise goes away, and you end up getting pretty nice depth of field, and it's easy to do. So the other thing is, yeah, I sort of showed I was moving some objects around, but the system can handle dynamic geometry. Dynamic geometry is expensive, there's no doubt about it. There is a database to be updated in real time whenever things start moving, but we're still able to handle a lot of moving objects because of the nature of the database that our hardware uses. So if I were to say, go and select let me see. I believe that this will be the body of the red car. So obviously I can move things. Basically, our system is such that moving an object doesn't have any impact, any cost impact on any other objects that are not moving. So that's the basic step. The other thing is that doing rigid body transforms, so essentially translation, rotation, and scale is almost free in the system. Except for the time, obviously, to update our hardware's DRAM whenever the objects are moving. But even that's pretty fast. The other thing, though, the next step beyond that is fully dynamic geometry, where every vertex is moving fully independently. So if I were to go to here and select the twist shader, hold on here, car paint, it's picked up the weird car paint change I made. Let me delete it. There we go, the car body's now solid. And then I go to here and start twisting it. Play. So now what this is doing is it's basically running a vertex shader. If we look there, what the vertex shader is doing is it's applying kind of like a simple twist function to every single vertex on the car body and updating that on the fly. So the system can handle dynamic geometry. It's not that slow, but you know, it's not ready to go in a game console just yet. We're still a little ways from that, but it'll happen. Yeah, that's another thing. I think the water is also watching. There's basically all that happened when I hit play. There's a uniform that's being advanced, and I think a number of the shaders are probably latching onto it and updating their effect. The water itself is an interesting little shader. Basically, what it does. So what the water is basically doing is, again, it's using Perlin noise to produce that waveform for the waviness, and it's when a ray hits the water, it depends what kind of ray it is. So basically, when an I ray or any normal ray hits the water, what it does is it evaluates that wave function and then refracts the ray through the water and down it goes. But it also reflects a ray off the surface based on the Fresnel term. So if I go over and look at that, as I get more oblique against the surface, you can start to see the reflections being created there. And you'll also notice that there's actually lighting being created underneath. And the way we're doing that here, I mean, this is really just up to you to write your shaders whatever way you want. If I did that, let me go in there and take a look. What's basically happening there is when the shadow rays go up through the water, they're being attenuated, or their contribution to the sample is being modulated based on the same wave function of the surface. So it creates like a caustic effect. But those who've done caustics before in a production render will realize they generally use photon mapping for them and not done this way. But it's still, if for like a game quality effect to do sort of fake caustics, this would still be a heck of a lot less work than what you would go through in a rasterizer today to create the effect. Cool thing here is you don't need a texture to fake the caustics on every object that the light could interact with. It just works. It's doing both. It's doing both actually. It's actually amplifying. You can do that too. You can create a lot of pretty weird effects with it. Now the final thing to show is, people often think, well, ray tracing is like a photorealistic rendering technique, and a lot of the time that's what people use it for, but you don't have to use it for that at all. In fact, it can allow you to create non-photorealistic effects a lot more easily too. So let's say I wanted to do some of that. I'm going to go and hide that weird object. And I switch the lighting model out. So what this is going to do, I'm going to change a couple of things. I'm going to get rid of that HDR sky background that all the rays were hitting, and switch this to Toon. Now, what this is doing is a pretty different effect. Let's turn all that on. What this is doing is basically, you can see it sort of looks like a cartoon shaded effect. Let me increase the resolution a little bit. I'm just going to bring it up to 720p. It'll be a little more clear. What this is doing, so this is running at 720p right now. It's decently quick. Basically, what's happening here is the shaders. I've basically swapped out the GLSL shader. There's like one shader that has a function that evaluates the diffuse lighting, and what it's doing now is, if the cosine of the ray with the surface is kind of oblique, then it will sort of kill the ray, resulting in that black lining that you can see on sharp edges on the geometry. But then if it decides that no, I want to shade the surface, then what it's doing is any secondary rays that are cast off, their direction vector is then quantized into like several like bands. So it creates sort of a cartoony kind of look. Which is kind of neat. So like the interior of the car in particular, this is a technique actually in car design. There's a lot of people who really, in industrial design, that really want this type of a view because it gives them a better sense of how the objects are actually shaped that is sometimes better than a photorealistic shading of the surfaces. It actually ends up being kind of important. So yeah, easy to do that in this system. It's because it's fully programmable. So I think that's all I'm going to go into now on the demo. I want to go on now, before maybe some questions. I'd like to go into a little more about what we're doing here, and what applications it might have beyond maybe the obvious ones. So, what is it that's been limiting ray tracing's performance? Why is it slow? And I want to get into that a little. Ray tracing, in our opinion, used to be a compute problem primarily. If this was 1994, 1995, the way you'd make ray tracing faster would be to build a processor that had more floating point units on it. That would be a pretty good way to speed up ray tracing. However, now, if you look at a GPU, it has ridiculous amounts of compute on it. That really isn't the problem. You can pack a lot of compute onto a chip. And let's just say that what we've built isn't we aren't competing against Intel on like MIPS or anything like that. We're not just trying to pack more compute onto a chip. Ray tracing is essentially a database problem, and now that you can throw phenomenal amounts of compute at this, the problem becomes how do you get the scene data to those compute units and saturate them efficiently to be able to solve this problem. The database in this world of ray tracing, the things that are stored in that database include your scene geometry, the shape of things, and any vertex attributes that you might have. The shader programs themselves, so the code that runs once the rays hit things, and then of course the texture maps, which you obviously still need, those huge artist-generated images or random number tables or whatever else you're putting into texture maps. Those all comprise the database. And with ray tracing, unlike rasterization, you've got tremendous numbers of very high frequency and very small scattered accesses into a very large database. And that is why it's very hard to saturate today's stream processors at doing this type of ray tracing. Now, the types of queries that we've honed in on, we've looked at the ray tracing problem and kind of as a database problem, and what are the types of queries that it does? And it's actually this that our hardware is exceptionally good at. There's the ray query, which is the one that we were basically everything you saw there was all done with huge numbers of ray queries. The ray query, there's two different. We break that into two different types. There's does this ray, any hit or the closest hit is one, which is most common, which is here's a ray's origin and direction and maybe a maximum travel distance limit potentially, and we say, okay, what is the nearest piece of scene geometry to that ray's origin? That's a database query, and we're very efficient at doing that, and with our hardware design. There's also the interval test, where you have a ray beginning point and an end point, and you don't want to know what the closest object was, but you just want to know, was there something between here and here? So for ambient occlusion and shadowing, that's a very, very common query operation. Is there anything between here and here? The other type of query, which has, we believe, very broad applicability too, is the three-dimensional k-nearest neighbor query. So I have a point in three-dimensional. Let's say I have a database, not of triangles, but of just records in three-dimensional space. And let's say I want to do a query where I have a point in three-dimensional space, and I want to get the k, like let's say I want to get the 32 nearest points nearest to that point within some kind of a maximum search radius. This is often used in production rendering, where you have a database of what are called photons, and they're basically like little pre-cached fragments of light, which you then query. You do these k-nearest neighbor queries in and figure out all the photons within that range, and then you integrate them into the lighting. So you can essentially store incident radiance in the scene, and then look up and reduce the number of rays you cast. So our ASIC actually has built into its design the ability to be very efficient at these three-dimensional k-nearest neighbor searches. It's our intention in the future. We've been looking into the idea of making the queries themselves actually programmable. So our solution, like what we're actually doing here, I'm not going to go into the hardware design itself. It's just simply no time to do that here. But basically, our whole system is built around the ability to regather coherence among those many queries. So you've got a whole bunch of queries coming into the database, and those queries are essentially random. They're all going to be pecking at different parts of the database. Our hardware and our algorithms implemented in that hardware are able to sort of gather queries that tend to be moving in similar directions inside that database. So it'll actually push it has a whole bunch of queries in flight at any one point in time, like many, many thousands of them, and essentially is able to schedule in and out any one of those queries and group them together when a set of queries are all going to access or need to test against the similar things. Our hardware basically is able to you can do that for locality of reference when you're accessing memory, but you also need to do that whenever you're trying to fill a SIMD register to do a very wide vector test. You can apply the similar concept of rescheduling work to be able to gather together operations all needing to be done on a common object. That's another thing that our hardware does. And then, of course, since we're not doing the shading on our hardware, it applies, and after it's figured out what everything's hit and what the query results are, the results themselves are reordered based on the code they'll need to run on the GPU, so that there's locality of reference when the results get to the device that emitted the queries. So if you think about it not as a ray tracing machine, but as a more general engine, essentially you could use our system and our hardware design for problems with these types of characteristics, where the database size is too large to fit in any practical processor cache. The other important characteristic is that any in-flight queries can't themselves edit the database. So you need the database to remain static for the duration while those queries are in flight. You can't modify the database where any one of those queries could end up needing to go there. That would be a disaster to try to do that. However, you can do things like edit other parts of the memory. Like you could double buffer, you could have animation going on, and you could be updating a different half of the hardware's DRAM, as long as you could guarantee that none of the in-flight queries would need to touch that part you're editing. Your problem had best have millions of independent queries a second. The queries in our system are completely not coupled to each other, so we've actually you need to have a heck of a lot of queries in order for this algorithm to work, because it needs choices. And the other thing you better not care about is the order of the results. So, think about emitting queries to a database and not caring about when you're going to get any particular result back. The order can be extremely random. But the benefit is that there's locality of reference in the order the results come back in. And the memory bandwidth of those database queries is orders of magnitude lower than it would be if you did it in a naive way. Finally, the ASIC itself. So that was FPGA-based hardware running there. The Caustic 2 is what we're calling it. This is the one that we fully intend to sell to as many people who will find use for it. It's ASIC based. It'll be running at about 3.5 times the clock speed and has 4 times the logic of the FPGA. So we're looking at about a 14x throughput increase with the ASIC that we're creating. So what you saw here today was doing its shading on a 8-core Nehalem Intel processor, and then compared with our hardware. You won't want to be doing your shading on the CPU. We're writing an OpenCL backend right now from our GLSL compiler, which maps the shading to a GPU, and that is required to pair with the Caustic 2 hardware, just because its throughput of queries is so fast that you need a pretty serious piece of compute to be able to do the shading. So we're pairing that with a GPU. It will work with the CPU, but I would imagine in some cases you'd be CPU bound. It's a 16-lane PCI Express card, still single slots, still bus powered, and if you've developed apps for Caustic GL now, it's a transparent upgrade. There's no changes required to your software. So that's the end of the presentation. I guess any questions?
When will this be going into laptops?
That's an interesting question. The question was, when will this technology be going into laptops? It's entirely practical for it to go into laptops. I think the bigger question is, when are there enough applications running on top of it that people who own those laptops say, I want ray tracing acceleration in my laptop?
Well,
yeah.
They'll be playing Second Life.
Yeah, well, people need to use it, and then it'll go into laptops quite quickly. There's no real technical reason why that, people pack enormous GPUs onto laptops today, so really this should be part of a GPU, I think.
So you say you've been mostly looking at professionals and trying to work people out. When do you hope to maybe go to the game industry and try to get some of those players?
Yeah, well, we think that the biggest...
Repeat the question.
Oh. the question, as I understood it, is in my presentation I said that we're initially targeting 3D professional. The question was, when are we going to be looking at gaming applications for the technology? Is that okay? You know, I would love it if this was in a console and we could scale up our architecture and actually just go all the way with this, but there's practical constraints there that limit that. However, there's a step, I think, before this actually is in the actual hardware that the gamers are using, and there's two interesting things. One is, like I was saying, the ability to accelerate the ability to bake those assets which are used for the games. We are actively looking at that right now. If anyone has applications where they use ray tracing to produce assets that'll be ultimately rasterized, you could use it now, and we'd be more than happy to talk. The other interesting aspect is sort of this move towards certain type of games I think can be playable online, where the rendering is done server side and the content is then delivered to the end user with a thin client. You know, there's some evidence that may become increasingly more practical, and I think our technology right now, instead of having to figure out how to get it to consumers in their devices, you know, it'd be a lot easier to put it in a server farm. And basically what this would do is it would very much increase the density of the number of users that you could in an interactively ray traced session in a server farm. So it would be like a power consumption and area conservation. And I think that's a way that it could potentially end up in gaming far, far sooner. Again, we'd need to talk to people who see applications there. We're really excited about it.
To be clear, though, we see the obstacles between us and gaming as not being necessarily technical. You've got sort of a chicken and egg problem. You have enough of these cards in the field for gamers to feel it's worth writing games, and you have enough gamers who are willing to buy these cards given the amount of games that are available. I think the technical hurdles could be overcome if the market were there.
Yeah.
What was the poly count of that scene and how many frames per second were you doing?
The poly count, I'll give you just a rough overview of it. The polygon count was 5 million. So there were 5 million triangles in the scene. When I was moving any of the geometry, the actual actively number of dynamically manipulated triangles was on the order of about 50 to 100,000 that were actively being dynamically manipulated at any point in time. The number of rays per pixel, which is a really important one, like how many actual rays were being involved. On average there, the ray per pixel was sort of between 5 and 10. When I turned the quality up to where all the noise went away, it was sort of around 16. Frame rate, yes, the frame rate, well, I guess I should do it again. I don't know. Yeah. Certainly at 720p. We generally do the interactive demonstrations at about VGA resolution. So yeah, it looks like it's about 7 frames per second. Yeah. Well. Yeah.
Maybe one more question.
Yeah, absolutely.
One of the other reasons people use ray tracing is for like complex services, like nerves.
Yeah.
Or those sort of things. You guys thought about that?
Yeah, we've thought about it. Our answer to that is as follows. You know, right now our fast path is triangles. However, we are, like I was saying about the queries potentially becoming programmable in the future, we are looking at the idea that the actual testers themselves could be programmed. But right now, you actually could intersect surfaces that weren't simply triangles by creating a shell out of triangles, and once the ray shader runs inside of there, you can do ray marching to do like voxel rendering. You can do that right now, or you could represent a NURB surface and actually intersect it within the ray shader, so you can procedurally intersect things there. But you would need to sort of bound the area of space that could contain those complex objects with like a box, if that makes sense. And you would still gain the locality of reference. Like the underlying algorithm would still take those rays and gang them together and schedule them for shade at the same time. So you'd still get the benefits, but the answer is our system really works in triangles. Okay.